Hello everyone, welcome to venkatvarmachemistry YouTube channel. In this session, we are going to learn geometrical isomerism in very short revision. Yes, first of all, what is stereoisomerism? Stereoisomerism, they are having same molecular formula, same IUPAC name, but different in spatial arrangement. Those isomers are stereoisomers. The phenomenon is known as stereoisomerism. Let's move on our geometrical isomerism. See, before that, configurational isomerism. So, what is configurational isomerism? See, configurational isomerism means the isomers which differ spatial arrangement of atoms and different properties. They are having carbon-carbon single bond, carbon-carbon single bond, free rotation. See, configurational isomerism means, see, the stereoisomers which differ in spatial arrangement of atoms, groups and different properties. These isomers cannot obtain free rotation around the carbon-carbon single bond. Carbon-carbon single bond is free rotation. That is what, see, for example, CH3, CH3. It is what? Carbon-carbon single bond. It is what? It is a free rotation of molecule. Free rotation of molecule cannot obtain by this configurational isomerism. See, configurational isomerism is classified into two types: geometrical isomerism and optical isomerism. Geometrical isomerism and optical isomerism. Let's move on geometrical isomerism. See, geometrical isomerism, it is also known as diastereomers or non-mirror images. Geometrical isomerism, it is also known as what? Diastereomers and non-mirror images. See, what is geometrical isomerism? See, have a look at for CH2 double bond CH2. Carbon-carbon having the double bond. Carbon-carbon having double bond, it is a restricted rotated. What is mean by restricted rotation? Not rotate the carbon-carbon double bond. See, restricted rotation. Carbon-carbon having the restricted rotation. So, carbon-carbon having the restricted rotation, they can show geometrical isomerism. Isomers which arises due to restricted rotation. See, what is the first point? The isomers which arises due to restricted rotation. See, restricted rotation present in alkene, carbon-carbon double bond, and oximes, carbon double bonded with nitrogen with OH, and rings. See, have a look at for the second point. See, restricted rotation present. Where it is present? Restricted rotate in alkenes like carbon-carbon double bond and oximes. Oximes means carbon double bond with nitrogen. Oximes and nitrogen double bond with nitrogen, azo, and carbon double bond with oxygen. It is a special case of geometrical isomerism. And rings means like cycloalkanes. See, what is the condition shows? The molecule is a restricted rotation, carbon-carbon having the double bond, oximes, carbon double bond with nitrogen, and a nitrogen double bond with nitrogen, and a carbon double bond with oxygen, and ring cycloalkanes shows geometrical isomerism. See, have a look at for the what are the condition for shows geometrical isomerism. What are the condition for the shows geometrical isomerism? See, what are the first condition? The condition is the molecule must have carbon-carbon double bond. See, molecule must have carbon-carbon double bond. Carbon-carbon double bond. What is the second condition? See, carbon-carbon double bond with restricted rotation site be different groups. See, restricted rotation site must be different groups. Say for example, have a look at for the example. See, for example, this carbon having A, B, and this carbon has A, B. Restricted rotation site means this site carbon having two different groups. This site has carbon having different groups. So this can shows it can shows GI. See, if carbon double bonded with carbon, it is AA, it is also AA. This carbon having same type of groups, this carbon side has same type of group. It not shown GI. Yes. See, have a look at for the next example. See, carbon-carbon double bonded AA and BA. See, for example, this carbon have same types of groups. This side has same type of groups. It can't show no GI. See, have a look at for the example. For example, carbon-carbon double bond. It is hydrogen. It is a hydrogen. It is a methyl group. It is hydrogen group. So this restricted site having different groups. This restricted site having same group. It not shows GI. It not shows GI. If carbon-carbon double bond, it is chlorine OH and methyl and H. This rotation site having different groups. It is methyl group, it is hydrogen, it is this site has two different types of groups. It can shows GI. Yes. See, have a look at for this. For example, carbon double bond with nitrogen, lone pair with hydrogen, it has H, it has methyl group. So this side has different types of groups. This side has different types of groups. It can shows GI. Yes, it can shows GI. Now coming to carbon double bonded with nitrogen, it is CH3. It is lone pair and H and H. So this head has same type of groups. This head has different types of group. So it not shows GI. See, have a look at for the example. See, if carbon double bonded with nitrogen with OH with a lone pair, it has CH3, it is H. So the restricted site having different types of groups, CH3H, and nitrogen has one lone pair and OH. It can shows GI. Yes. See, have a look at for the example. Have a look at for the next example. Nitrogen with nitrogen double bond with nitrogen having lone pair and H and H. See, this nitrogen having different types of groups. One is hydrogen, other one is lone pair. This nitrogen has two different types of groups. This site has different, this site also different. It can shows GI. It can shows GI. Yes. Have a look at for the next example. See. Carbon double bond with oxygen. Carbon double bond with oxygen and H and methyl. See, this carbon side has different types of groups. So this oxygen has two different types of groups. It can shows GI, special case of geometrical isomerism. See, have a look at for the next example. If carbon double bonded with carbon having, see, it is fluorine, it is chlorine, it is bromine, it is iodine. So this side has two different types of group. This side has two different types of groups. It can shows GI. Yes, no doubt it can shows GI. See, have a look at for the next example. See, if carbon double bond with nitrogen, it has lone pair, it is OH. See, this carbon site double bond, these two CH2, this is a CH3 and a H. So this carbon has different types of groups. So it can shows GI, it can shows GI. Yes. See, have a look at for the carbon double bond with OH and lone pair. These two are geometrical isomers. Yes, these two are geometrical isomers. It can shows GI. Yes, it can shows GI. See, have a look at for the next example. See, in rings, monosubstituted ring. See, in monosubstituted ring, monosubstituted ring like this, monosubstituted ring, no GI. It cannot shows GI. See, like this, monosubstituted ring cannot shows GI. It cannot shows GI. For di, tri, tetra. See, di, tri, tetra substituted groups can shows GI. It can shows GI. It can shows GI. See, have a look at for the example. See, if I am taking example, see, cycloalkanes having, see, it is the CH3, it is a H, it is a CH3, it is a H. So two different types of groups. It can shows GI. Yes. See, look at for the example. It is CH3 H, it is the CH3 H. These two are shows GI. Yes, it can shows GI. It can shows GI. See, have a look at for the next example. See, methyl H and methyl H. So this restrictor rotation having two different types of groups. See, one is a methyl hydrogen. It can shows GI. Yes, it can shows GI. See, have a look at for this. This can shows GI. No, it cannot shows GI. No GI. See, now look at for one more example. See, it is the CH3, H and it is Cl H. The restricted rotation having two different types of groups, ClH and CH3H. It can shows Gi? Yes, it can shows Gi. See, have a look at for the cycloalkene. In cycloalkene, look at for the dash wedge formula. See, in dash wedge formula, see this restricted rotation having two different types of groups. Two different types of groups means it can shows Gi. It is both are same. Both are same. See, look at for this methyl and hydrogen, hydrogen and methyl. This can shows Gi. Yes, it can shows Gi. It can shows Gi. See, this is the dash wedge formula. Dash wedge formula. See, have a look at for some more example for Gi exhibit or not. See, look at for the example. Have a look at for the example Gi exhibit or not. See, in carbon-carbon double bond restricted rotation, it is hydrogen, it is methyl. Yes, it can shows. Yes. See, this double bond restricted rotation, methyl group and a hydrogen group. Yes, this double bond having H and methyl group and hydrogen and this group, it can shows Gi. Yes, have a look at for the next example. See, carbon double bonded with nitrogen. See, carbon double bond with nitrogen. It is phenyl group and hydrogen. It is OH and H. See, two different groups. It can shows Gi. Yes, it can shows Gi. Yes, have a look at for the next example. See, nitrogen double bond with nitrogen having phenyl and these are the lone pairs. These are the lone pairs means always shows geometrical isomerism. See, look at for this is the restrictor rotation having it is H and it is CH3, different types of groups. See, this carbon moves this carbon having CH2 group, this carbon moves this side methyl and hydrogen, it can shows Gi. Yes, it can shows Gi. Have a look at for this. Have a look at for this. Carbon double bonded restrictor rotation. It has hydrogen, it has hydrogen, it has hydrogen, it has hydrogen. Can't shows this Gi, but this CH double bond NH, this can shows Gi. Yes, it can shows Gi. See, look at for the next example. This is a restrictor rotation, hydrogen and CH3. This carbon move this side, it is CH2. This carbon moves this side, CH2. So both are same. We can move next carbon. Next carbon has it is methyl group. It is hydrogen, hydrogen and methyl group. So we can move this carbon. It is CH2 group. CH2 group means it can shows Gi. Yes, it can shows Gi. It can shows Gi. See, have a look at for the cis and trans isomerism. Cis and trans isomerism. See, what is cis isomers? See, similar groups atoms like in same side of double bond are called cis isomers. Cis isomers. See, like carbon double bond, carbon double bond with similar groups. For example, it is CH3, it is H, it is CH3, it is H. Same groups are arranged in same side, that is a cis. That is a cis. Otherwise, trans, carbon double bonded, carbon double bonded with it is CH3, it is H, it is CH3, it is H. These groups are arranged in opposite side. See, same groups are same side, that is cis. Same groups are opposite side, that is a trans isomerism or trans isomers. Trans isomers. See, have a look at for this example. See, it is chlorine, it is hydrogen, it is chlorine, it is hydrogen. Same groups are same side. It is what? Cis. See, it is H, it is Br, it is Br, it is H. same groups are in opposite side, that is a trans. That is a trans. See, have a look at for this example. See, carbon double bonded with carbon having same type of group, same side, that is cis. Opposite side carbon double bond, it is what? Trans. Trans. This is a pattern. See, identify cis and trans. See, identify cis and trans. See, carbon double bonded with carbon, it same type of groups arranged in same side, that is a cis. Different types, it is hydrogen, it is hydrogen, it can shows trans. I will look at for this cyclic. So same, see, carbon double bonded, it what? It is cis, it is a cis. So it is cis, it is a trans, it is a trans. I will look at for this example. See, methyl group and methyl group both are having same side, that is a cis. So this has, see, both are opposite side, it is what? Trans. It is a trans. See, if aerial distance must be different in GI. Aerial distance means, for example, methyl group, methyl group. So it is a what? It is a x distance, and methyl group and methyl groups, it is diagonal, it is a y distance. So x is not equal to y. X is not equal to y. Aerial distance must be different in geometrical isomers. This is a condition shows geometrical isomers. See, have a look. If carbon double bonded having four different types of groups, for example, it is fluorine, it is chlorine, it is bromine, it is iodine. So it can shows GI, but cis and trans is not possible to give this compound. Now we can use EZ nomenclature, the nomenclature of EZ nomenclature. Let's move on EZ nomenclature. See, EZ nomenclature, CIP rules, SIP rules. What is SIP? Con, Ingold, Prelag. See, look at for EZ nomenclature. See, if two senior groups are same side of restricted bond, the configuration is Z. The configuration is Z. Z for Josamine, it means together. Otherwise E means antigon, it means opposite. It means opposite. See, the restrictor rotation of carbon double bond having higher priority, this is a lower priority, it is a higher priority, it is a lower priority. See, high priority groups are arranged in same side, that is a Z isomer, that is a Z isomers. And high priority groups are arranged in opposite side, that is a E, antigon. Antigon means opposite, it is a E isomer, it is a Z isomer, Z isomers. See, look at for example. See, the high priority and low priority of carbon double bond, how to decide? By using SIP rules, Con, Ingold, Prelag rule. So we can follow rules, we can decide the E and Z isomer. Look at for rules. See, SIP rule, higher atomic number to get a higher priority. For example, hydrogen, carbon, nitrogen, oxygen, fluorine, sulfur, chlorine, bromine, iodine. Which is more priority? Is the higher atomic number is a more priority. Higher atomic number to get higher priority. See, iodo is most priority. Then bromine, then chlorine, sulfur, fluorine, oxygen, nitrogen, carbon, hydrogen. If carbon double bond, it is iodo, it is bromo, it is fluoro, it is chloro. So iodo bromo, which is high priority group is the iodo, and it is the second priority. fluoro, chloro, which is higher priority, chlorine, it is second priority. So high priority groups are opposite. It is what isomer? It is E isomer. Look at for this. This carbon has iodo and bromo. First priority, second priority. It is first priority, it is second priority. So it is what isomer? It is a Z isomer. It is a Z isomer. Look at for this example. This carbon double bonded with carbon. It is hydrogen, it is bromine. First priority, it is a second priority. So nitrogen and carbon, what is the most priority? Nitrogen, and after that carbon. So it is what? Opposite side. So the isomer is what isomer? E isomer. E isomer. It is a E isomer. It is a higher atomic number to get higher priority. Look at for second rule. Coming to second rule, if atomic number of first atom is same, then go for next atom and apply rule 1. See, carbon carbon double bonded with carbon and carbon, both are having same atom. So we can go for next atom, what? Carbon. 3 hydrogens, 3 hydrogens. Yes, here 3 hydrogens, 3 hydrogens, here 2 hydrogens, here 3 hydrogen. Which is most priority? It is the first priority and it is the second priority. And nitrogen, hydrogen, more is the nitrogen, hydrogen is a less priority. See, if carbon double bonded with carbon double bond having the same atom, then go for next atom. Next atom, here 2 hydrogens, here 3 hydrogens. After 2 hydrogen, who comes? Carbon comes. First priority. So what isomer? It is 1 and 1. Opposite side, it is E, antigon. Yes, like this. For example, CH2 Cl, CH2 OH, yes, and CH2 NH2, okay, and CH2 CH3 and CH3. So which is most priority? Chlorine, here oxygen, here nitrogen, and carbon with carbon C, and hydrogen, which is most priority, and most priority is the CH2Cl. Have a look at for the next rule. In case of isotope atomic number same, higher mass number get higher priority. In case of isotope atomic number is same, higher mass number is a higher priority. So it is hydrogen, deuterium, tritium. Hydrogen mass is the 1, deuterium mass is the 2, tritium mass is the 3. See, if carbon double bonded with carbon, hydrogen, deuterium, which is the most priority? Deuterium, after that hydrogen. So CH3, it is CH3 with 14, C14, C12, which is most priority? C14 isotope, after that C13 isotope. So what? Same or high priority groups are same side. It is what isomer? It is a Z isomer. It is a Z isomer. Yes, have a look at for the next rule. See, if groups containing double bond or triple bonds are present, they are considered to be duplicate and triplicated. See, carbon double bonded with Y, it can be written as, it is treated as carbon with Y and carbon with Y and Y with carbon. So it can written as C with Y, carbon double bonded with Y, carbon double bonded with Y, and Y double bonded with carbon. And C triple bond Y is treated as, written hypothetical as carbon with Y and carbon with Y, carbon with C and carbon with C and carbon with Y. Look at for the CO, carbon double bonded O, and CH treated as CO, carbon with O and oxygen with O. Yes, and carbon triple bond N is treated as carbon with nitrogen and carbon with nitrogen and carbon with carbon, carbon with carbon, carbon with nitrogen. See, double bond is duplicated, triple bond is triplicated. Yes, look at for the next rule. See, if double bond, triple bond, see, it is carbon triple bond with carbon, carbon double bond with carbon. See, carbon triple bond with carbon treated as, see, carbon, carbon with hydrogen, carbon with carbon, carbon and carbon. It is a triplicated. So carbon double bonded with carbon, CH double bond CH2 treated as carbon with carbon, two hydrogens and hydrogen and carbon duplicated. So bond pair is senior to lone pair. Bond pair is senior to lone pair. Look at for the next. If one of the position is occupied, lone pair like oximes, azo compounds is given by high priority. High priority. See, look at for examples. Look at for carbon double bond with nitrogen means oximes. In oximes we can use syn and anti. What is syn? See, carbon double bonded with carbon, hydrogen atom and OH as in same side, that is a syn. Syn is nothing but a cis. It is a acetaldioxime. It is a acetaldioxime. Look at for this compound, carbon double bonded with a hydrogen and OH as in opposite side, that is anti, nothing but a trans acetaldioxime. Yes. Now look at for the carbon double bonded with nitrogen, hydrogen and OH as same side, that is a syn benzoyl dioxide. Yes, hydrogen and OH is in opposite. It is anti-benzoyl dioxide, nothing but a trans benzoyl dioxide. Yes, see. Look at for example, carbon double bond with nitrogen. See, lone pair and which and CH3 and C6H5. See, it is what? See, syn methyl phenyl ketoxime. Methyl phenyl ketoxime. Now it is CH3 OH anti methyl phenyl ketoxime. Yes. Now nitrogen double bond with nitrogen, what? It is azo, syn, same side, it is a syn azobenzene. It is what? Anti azobenzene. See, physical properties of geometrical isomers. Say carbon double bonded with carbon, it is bromine and hydrogen, bromine and hydrogen. See, carbon and bromine, which is more electronegativity? Bromine, it moves this side. Carbon and bromine move this side. It is what isomer? It is cis isomer. Cis isomer is mu is not equal to 0. Yes. Now carbon bromine move this side. Carbon, see, it is what? It is trans. In trans, what happened? The resultant dipole moment is cancelled out. So it is what? Mu equal to 0. For cis, mu not equal to 0. Trans, mu equal to 0. Cis has more dipole moment than trans. Why? Cis isomer resultant mu not equal to 0, while trans isomer dipole moment mu equal to 0. Yes. See, dipole moment of cis isomer is greater than trans. Cis isomer resultant dipole moment, while trans isomer dipole moment cancel out. This is related dipole moment property of geometrical isomer. Have a look at for boiling point. See, cis isomer is greater than trans isomer due to molecule having dipole moment is higher boiling point due to larger intermolecular force of attraction. For the boiling point is cis is greater than trans due to molecule having dipole moment, higher boiling point due to larger intermolecular force of attraction. Then solubility. Solubility in water, cis is more soluble than trans due to more polar molecule are more soluble. More polar molecule is more soluble. Look at for melting point. In melting point, trans isomer are more melting point than cis due to more symmetric isomer, higher melting point due to better packing in crystal lattice. Trans isomers are more symmetric than cis. Melting point of trans is greater than cis due to more symmetric isomers are having higher melting point due to better packing crystal lattice. Trans isomers are more symmetric than cis. This is about melting point. Now coming to stability. See, in stability, trans isomer are more stable than cis due to molecule having more van der Waals strain are less stable. More van der Waals strain, less stable. In cis isomer, the bulky groups are closer. They have larger van der Waals strain. Van der Waals strain. That's why trans is greater than cis. On moving from calculation of number of geometrical isomer. So how to calculate number of geometrical isomers? Calculation of number of geometrical isomers. See. Case 1. When molecule is unsymmetrical, endopollines are different. Molecule is unsymmetrical, the endopollines are different. We can calculate the number of geometrical isomer is 2 power n. N is a stereogenic center. N is a stereogenic center. See, look at for example. See, both ends are different. Yes, it is bromine, it is methyl. So it is what? Unsymmetrical. Endopolline groups are different and unsymmetrical. What is the n value? N value will be 1, it is 2, it is 3. How many stereogenic center? 3. So number of geometrical isomers possible in 2 power n or 2 power 3, it becomes how many number of isomers? 8 isomers. Calculation of number of geometrical isomer. When molecule is unsymmetrical, end groups are different, we can calculate the number of geometrical isomer is 2 power n. Look at for the case 2. See, in case 2, when molecule is symmetrical, end groups are same. Molecule is symmetrical, end groups are same. The number of geometrical isomers is 2 power n minus 1 plus 2 power n by 2 minus 1 if even number of stereogenic center. N value will be even. We can use geometrical isomer is 2 power n minus 1 plus 2 power n by 2 minus 1. Look at for example. For example, endopollines are same. Yes, endopollines are same. So number of stereogenics are 2. So n value will be 2. Substitute the principal. Geometrical isomer is 2 power n minus 1 means 2 minus 1 plus 2 power n by 2 means 2 by 2 minus 1. So it is what? 2 minus 1, 1, 2 power 1 plus 2 power 2 by 2, 1, 1 minus 1, 0. 2 power 0 equal to 1. So it is what? 2 plus 1, it is 3. Number of geometrical isomers are 3. Have a look at for case 3. When molecule is symmetrical, endopollines are same. So the odd number of stereogenic centers. So we can calculate geometrical isomer equal to 2 power n minus 1 plus 2 power n minus 1 by 2. This principle we can use when symmetrical molecule endopollines are same and odd number of stereogenic centers. See, endopollines are same, is same. Number of stereogenic centers 1, 2, 3. 3 means what? Odd number. Number of geometrical isomer is 2 power n minus 1 means 3 minus 1 plus 2 power n minus 1 by 2 means 3 minus 1 by 2. 3 minus 1 means 2. So 2 by 2 means it is 2 power 1. So 2 power 3 minus 1 means 2 power 2. 2 power 2 means 4, 2 power 1 means 2. Number of geometrical isomers are 6. So this is a way to calculate number of geometrical isomers. Number of geometrical isomers. Yes, this is for complete geometrical isomerism in short revision. Thanks for watching.